Okay, so hopefully my audio is working now. And let's go over Ohm's law. So Ohm's law is an equation that it's indicative of the same relationship that you all have been investigating in the first part of your work for this week. So you all were looking at the relationship between current and resistance, and Ohm's law gives us the relationship between those two things along with voltage. So in our equation we have V for voltage is equal to I, which is sort of strangely for current, and it's current times, more predictably, for the resistance, and R. So this equation gives us a relationship between those three most important quantities that we talked about on Monday of this week: voltage, current, and resistance. As a reminder, voltage has to do with our battery, so it depends on the amount of charge stored up on each terminal of our battery, the physical separation, the quality of an insulator between those two terminals. We might talk more about sort of what determines these voltages, but for now it's important to know that this voltage, sort of the cause of the energy in our system, is from the battery. Current is the flow of electricity or of electrons in our circuit, and resistance is any impedance or obstruction to the flow of current or the flow of electrons. Now, the way that I tend to prefer to think about this equation, because I think it shows the cause and effect of these different things a little better, and this is the exact same equation as what we have with this V equals IR. It's just a different way to show it, just an algebraic manipulation away, is that I, the current, is equal to our voltage over resistance. And the reason that I like this one better is because I tend to think in terms of current as sort of like the effect. You know, if you provide voltage to a circuit and if you provide resistance, current will flow and electrons will flow through the wires and through any elements that we have in that circuit. And so this fraction, the current being equal to voltage divided by resistance, voltage being in the numerator means that if our voltage goes up, this number is going to go up too. Like 1/5 is smaller than 2/5, and if we increase that to 3/5, if this voltage went up to 3, then the current would go up too. And similarly, if we have resistance in the denominator of this fraction, as the resistance or obstruction to current flow goes up, as the things that block electrons from moving increase, there will be less current, and that's in the denominator of our fraction. So that's like how 1/7 is a lot smaller than 1/2, or 1 over a billion would be much smaller than 1 over 3. So as this resistance goes up, we see our current go down, and that's the trend that you all found earlier this week. Okay, so now the rest of this video, I'm going to do a couple example problems for how we use Ohm's law. It is one of the simpler algebraic equations that we have worked with this year. You all have worked with some pretty complicated equations and solved some pretty complex problems. Luckily, at least, even though this is conceptually pretty complicated and definitely very important, it's not one of the more difficult equations that we've worked with this year. So if you're someone who doesn't struggle with the math of our class, then you probably don't need to watch this, or you might not need to watch this. And if you're someone who does tend to struggle with that part of the class, certainly think about sticking around. So let's say that we have a battery that is 10 volts, and we have a light bulb that has a resistance of 4 ohms. And the question for us is, what is the current going to be that flows through this system, that flows through that circuit? And so I'm just going to plug in the stuff that we know into this equation. So we know the voltage, the V, is 10 volts. That's the strength of our battery. We know that the resistance is 4 ohms, but we don't know what that current is. So I'm just going to leave current as I, since we don't know it. I'm just going to leave it as its variable and plug in the 4 ohms that we do know for that resistance. And then to solve this, we've got I times 4. They're right next to each other, so they're being multiplied. And to cancel out that 4, we have to do the opposite of multiplying them together and divide by whatever is being multiplied by this I. So we're going to divide both sides by 4. So the 4's go away over here, and we do 10 divided by 4 to get that. Our current is equal to, looks like that would be 2.5 amps, or 2.5 amperes. And so these sort of most basic problems with Ohm's law are pretty much plugins to our equation where we would know any two pieces of this equation, and we would just have to solve for our one missing unknown. So let's go through just a couple more examples of how we would solve for the other thing. So we just did an example where we solved for a missing current. We could also do a problem where we solve for a missing voltage. So let's say someone has given you a task and they need you to run 8 amps of current through their circuit, and they currently have a resistance or some object that they're trying to power, and that object has a resistance of, let's say, 12 ohms. And the question is, how strong or what voltage does the battery that you are going to put into the system need to be? And again, we're just going to plug in the stuff that we know, and we're going to leave anything that we don't know as a variable or as its symbolic representation. So we don't know the voltage. I'm going to leave that as V. We do know the current is 8 amps, so I'll plug that in for I, and we know the resistance is 12 ohms, so I'm going to plug that in for our R. Now, in the previous example, we had to do a little bit of manipulation since we had an I that was not isolated. It was stuck being multiplied by some number. But here we already have what we're trying to solve for isolated on its own side, so we don't actually have to do any algebra here. All we have to do is take our 8 and 12, and since they're right next to each other, we need to multiply them together. So that should give us, I think, 96 volts as the strength or as the voltage of our battery. It's a little confusing because the unit and the dimension symbols are the same, so this looks a little repetitive. 96 volts is the voltage in our battery. That looks a little weird, but that is technically correct here. Okay, so one more example where we're now going to solve for the one other thing that we haven't solved for yet. So we've done a problem where we solved for a current, we've done a problem where we solved for the voltage, now we're going to do a problem where we solve for a missing resistance. And we could have done this, we would have done this in lab if we were still in class, where if we know that, let's say we have a 9-volt battery, which is a pretty common battery, that's what we would have used in class. So we have a 9-volt battery. We use an ammeter, which is what you all have been using in the simulation to measure a current. And let's say that the ammeter showed us a current of, let's say, 2.25 amps is our current. And the question is, what's the strength of the resistor, or how much resistance does some object or element in our circuit provide? So again, we're going to plug in the stuff that we know. So this V we do know is 9 volts. That's the strength of our battery. We know that the current is 2.25 amperes. We measured that and determined that experimentally. And now the question is, what is this missing resistance in our equation? And we don't have our R isolated yet, so we've got to do one algebraic step, it looks like, if we want to isolate this. And right now, R is being multiplied by 2.25, so if I want to get rid of that 2.25 to get the R on its own side, we've got to divide both sides by the 2.25, so that'll get rid of the 2.25 on this side, and then we need to do 9 divided by that 2.25. And I believe that when we do that, that should hopefully get us, and if my math is wrong, I'm sorry, that should get us a 4 ohm strength for that resistor, or 4 ohms of resistance are provided by whatever element we have within this circuit. So Ohm's law is, again, an incredibly important conceptual relationship, and certainly one of the foundations of physics, and definitely one of the foundations of electricity and magnetism. But for us, it's at this point a very simple, relatively simple equation for us to work with, but it allows us to do a lot of things in our work with circuits.